Hello, so my name is Gary Powers. I teach physics at the South Hills School of Business and Technology, and this is a post-secondary school. So the purpose of this video is to describe a fluid pressure measurement lab that could accompany a physics course. And so this could be appropriate for the high school level or for the associate degree level or even a four-year degree level. So this is part one of three. For this first part is to describe the concept. Part two will describe an apparatus that you can assemble for use in the lab. And then part three will demonstrate the actual performance of the lab using the apparatus. Okay, so here's the objective of this fluid pressure lab. So the idea is to confirm that the textbook method of calculating fluid pressure is accurate. So that fluid pressure textbook calculation is equal to fluid density times the depth of an object within the fluid. So we want to see, so we've been performing those calculations, but the question is, does that calculation really produce an accurate fluid pressure? So here's some credits for this lab. The current textbook we're using is Physics by Paul Tippins. We've used that for many years. But the inspiration for developing the lab exercise was a 1954 text written by White and Manning, and it was a lab manual. And so this lab actually was described in there, but the apparatus for it is not readily available, but it's pretty simple to produce and assemble. All right, so calculation of fluid pressure. So fluid pressure, as we saw in an earlier slide, was fluid density times the depth within the fluid. It could be the depth at the bottom of a floating object or just any depth within the fluid. And that equation is P is equal to D density times H, which is depth. So H is used, I assume, because you don't want to have two different D's in the equation and get confused. So H is actually the depth within a fluid from the surface of the fluid. And then you have the fluid pressure actually pushes upward on an object, on the bottom of an object that's floating in a container of fluid. And this sketch is a rough sketch of the apparatus we'll use, and it gives you the flexibility to change the weight of that object, as we'll see later. So here's an example. We just said that the calculation of fluid pressure was equal to density times height, which is depth. So here's an example. So let's say you had a container of alcohol, and the density of alcohol, you can look up in a density table, is 49 pounds per cubic feet. And let's say in this example that at the bottom of this floating object is at a depth of 15.5 inches. So the density times the depth plus a conversion between cubic feet and cubic inches gives you 0.440 pounds per cubic inch. So that's how that fluid pressure is calculated. Now there is another type of pressure that influences fluid in a container, and that's described by Pascal's law. So this is related to atmospheric pressure. So if you have an open container, which we will with this apparatus, then the atmospheric pressure in the air is actually transmitted and felt equally throughout the container of fluid. And this is not depth related. So for example, an atmospheric pressure in English units would be 14.7 pounds per square inch, just for the average atmospheric pressure. So that atmospheric pressure is just felt and transmitted equally throughout the container. Again, not depth related. So that atmospheric pressure also is, is felt at the bottom of this floating object. However, it also means that this atmospheric pressure in the surrounding air is also felt and is pushing down on top of this floating object. So we're not going to take into account atmospheric pressure in this lab because the atmospheric pressure pushing down on the object is offset by the atmospheric pressure pushing up on the bottom of the object. So it cancels itself out. There's another way to calculate fluid pressure. And so we're making the assumption you have this floating object, and in an equilibrium situation, the pressure exerted by the object on the fluid is equal to the fluid pressure pushing up on the bottom of the object. So if we could calculate the force or the pressure exerted by the object on the fluid, that would also tell us what the fluid pressure is. And the way we would calculate the pressure exerted by the object in the fluid is to use the equation pressure is equal to force divided by area. In this case, the force is the weight of the object. So in this lab, you would weigh the object, so you'd know what the weight is, which is the force. And we're also using a cylindrical object, so the area, if you look down at the bottom of the object, the area is the area at the bottom of the object, which in this case is a circle. So the area at the bottom of the object is equal to pi r squared, the area of the circle. Now let's do an example calculation of the pressure exerted by the object on the fluid. Now this, I have not tried to make this example calculation correspond to the calculation we did a few slides ago. This is just another example with different given information. So let's say you have an object, this cylindrical object has a weight of 2 pounds, and it has a diameter of 2 inches, which means the radius would be 1 inch. So the pressure exerted on the fluid by the object would be equal to force divided by area, which is equal to 2 pounds divided by pi r squared, in this case 0.637 pounds per square inch. So then the question is, can we use that information to determine the H factor, how deep the object is resting in the water? So the fluid pressure is equal to the pressure exerted on the fluid by the object, and let's just continue with this example, 0.637 pounds per square inch. And in this example, rather than the previous example, which had a fluid of alcohol, we're just going to say that the fluid's water, which has a density of 62.4 pounds per cubic feet. And now let's predict how deep this object should be resting in water. So we're going to use this fluid pressure equation, P equals dH, but we're going to solve for the H term, which is depth. And we already know the pressure, which is this 0.637 pounds per square inch, which we calculated earlier, and we know the density of water. So the depth of the object in the water should be 0.637 pounds per square inch divided by the density 62.4 pounds per cubic feet, and you have to do a conversion between cubic feet and cubic inches. So that turns out to be 17.6 inches. Okay, now we would now get to the point where you would use the apparatus. So the next step is, using a lab apparatus, actually take this object and then place it in the container and see if it indeed rests 17.6 inches below the waterline. If it does, that means the accuracy of the fluid pressure equation is confirmed. Here's the apparatus we're using, and the next video, part 2, will describe all the different parts and how you might put this together. And there is a lot of flexibility to change the weight of this floating cylinder. And the last step in the lab is, since we have the flexibility to add different weights to this floating cylinder, then the lab calls for, I've set it up for 5 different weights. You can put a small weight in there and just keep adding successive weights and collecting data. So the graphing at the end is graphing fluid pressure versus the actual measured depth of the object, because the apparatus allows you to actually measure the depth of the object. So you graph fluid pressure versus depth. Then you can draw a best fit line to match the data points and then calculate the slope of the line. So since slope is equal to rise over run, which in this case is pressure divided by the depth, h, then using the fluid pressure equation, that slope is equal to the fluid density, or should be. So a part of the lab is to then compare this slope, which is the fluid density, to the actual fluid density, the textbook density of water, 62.4 pounds per cubic inches, or per cubic feet. All right, so in summary, the lab is meant to confirm the accuracy of the fluid pressure equation, calculate fluid pressure using the pressure exerted by the floating object in the fluid, graph the measurements and use the graph to determine the fluid density, and then compare that calculated density to the textbook density. All right, the next video, part 2, will be a description of the actual apparatus.